Hello everyone and welcome to this lesson. My name is Edmond and today we have an OSPF challenge or lab on load sharing with Not-So-Stubby Areas or NSSAs. The goal of this lab is to refresh our knowledge on some key OSPF concepts like NSSAs, Type 75 translation, and OSPF forwarding address. The main task or ask of this challenge, should you choose to accept it, is to ensure that R1 has two equal course paths, that is through R2 and R3, to reach the loopback 0 interface on R4. So you can pause the video and look at how you would address this in the context of these constraints, which is 1, area 34 should remain as a Not-So-Stubby area. R2 and R3 should remain as ABRs. We are not to configure, that is area border routers. We are not to configure any tunnels. We are not to use any other routing protocol. And routers in area 0 should remain in area 0. All right, so let's dive right in. The key to getting to the solution is to first understand how R1 is reaching the loopback 0 and R4. And most importantly, why it is making such a routing decision. The loopback 0 and R4, as we see right here, is 4.4.4.4/32. Because this is redistributed into area 34, which is an NSSA, we expect this to show in this area as a type 7 external route. So let's look at what we are seeing at this moment. If you look at the route table, first let's look at the route table on R4 for that specific prefix. It says that this is a directly connected network, that is loopback 0. And because we are redistributing this into OSPF, if we check the OSPF database, we see this as a type 7 external LSA, which is what we expect because area 34 is a Not-So-Stubby area. So we do not expect to see type 5 LSAs in this area. Now let's move to R2 and check our route table for R2. So let's look at the specific prefix 4.4.4.4. R2 says that I have length of this prefix and I length of it as a type 7 external route. So NSSA N2 to be specific. And I length this from 4.4.4.4, which is the router ID of R4. So if you look at the route table without the specific prefix, we can see right here that the prefix has been length right here 4.4.4, which is our prefix of interest, as OSPF type 7 external, N2 OSPF NSSA external type 2. Now let's look at R3. So we do show IP route 4.4.4. Same on R3 is been length as a type 7 external route, N2, also from 4.4.4.4, which is R4. Now let's move on to R1, which is our router of interest, and look at how R1 actually lengths of this prefix. So show IP route for 4.4.4.4. R1 says that I have length of this prefix, but as a type 5 external, that is E2. Remember, R1 sits in area 0. Area 0 cannot be an NSSA. Area 0, which is the backbone area, cannot be any form of a stubby area. What that means is that the type 7s that we length in area 34 For them to get to area 0, they have to be translated from type 7 to type 5. But here's the catch. Only one of these two ABRs, area border routers, actually does the type 7 to 5 translation. And this is the router that has the higher ID. So we are learning this as a type 5. We know that this is because of the type 7 to 5 translation. And this is being learned from 3.3.3.3 is the router ID of R3. Now let's look at the router IDs of R2 and R3. That is our area border routers. So IP, OSPF, let's include ID. So router 2 has 2.2.2.2. And if you look at R3, so IP, OSPF, and we look at ID 3.3.3.3. So because R3 has a higher router ID, it does by default the type 7 to 5 translation. That is why we are seeing this length from R3. But we are seeing that the next hop from R1 to reach 4.4.4.4 is actually 12.12.12.2, which is the path through R2. So that is the second why that we have to answer. Why is it that R3 is actually advertising this route or prefix to R1, but R1 is preferring to go through R2? The type 7 to 5 translation is a control plane construct. The fact that a router is doing the type 7 to 5 translation, and originating that type 5 does not necessarily mean that it sits in the data plane path to reach the prefix it originated. That still doesn't answer the question of why we are going through 12.12.12.2, which is R2. To answer that, let's look at our OSPF database on R1. So show IP OSPF database. Let's look at external for that specific prefix. Now, we see a field here, the forward address. The forward address is seen in external aliases, which is type 5 and type 7. It is the forwarding address that actually determines the path that the router would follow in reaching the prefix, which in this case are linked state ID of 4.4.4.4, our external network. So R1 is saying that, look, in my OSPF database, I have learned of this through R3, but if I want to actually forward traffic to this prefix, I need to go through 24.24.24.4. That's my forwarding address. But how do I get there? So if you look at show IP route for 24.24.24.4, it recurses to 12.12.12.2. That explains our second why. Why R1 goes through R2 to reach the loopback on R4, although R3 actually did the origination, or R3 is our advertising router. We still do not know at this point why the forwarding address on R1 is 24.24.24.4. But we've answered our first two questions, or our first two whys. The first why was why R3 was advertising it to R1. It is because one of the ABRs does this advertisement, and R3 does this in this case by default because it has the higher router ID. We've answered the second question of why R1 actually follows the path through 12.12.12.2 as the next hop to get to this prefix. The third why would get there. So now we know why R1 is not load sharing, but how do we get it to load share? Now, based on what we know so far, if we can manipulate the forwarding address such that R1 has two equal cost paths to reach the forwarding address, so at this point it has just one path. But if we can manipulate the forwarding address such that R1 has 2 equal course paths, then we can engineer load sharing from R1 through R2 and R3 to the loopback interface on R4. That's our first option. There's a second way that we can figure this out by suppressing the forwarding address during the type 75 translation and also asking both R2 and R3 to do that translation. We'll look at that in our next lesson. All right. So let's get to our third why. Okay. Our third why is basically why does R1 use 24.24.24.4 as a forwarding address. Now, there are some rules that govern how the forwarding address is selected. In this scenario, the prefix 4.4.4.4 is directly connected to our ASBR R4. It was redistributed from R4, and our forwarding address, as we saw, was an interface in Ethernet 0/0 on R4. Now, if there is a loopback, first rule, if there's a loopback configured in area 34, that is the area in which we originated that prefix, that loopback is selected as the forwarding address. In this example, we have only one loopback on R4, 4.4.4.4. This loopback, however, is not natively part of area 34. It was just redistributed into area 34. What this means is that it cannot on its own be a forwarding address. We need that loopback to be in area 34. We don't have that now. So we fall back to the second condition. If this first condition is not met, then the first IP address of our OSPF interface list is selected as the forwarding address. So if we come to R4 and we look at show IP OSPF interface brief, our very first interface here is Ethernet 0/0, and the IP address on this interface is 24.24.24.4. That explains our third why. Because there was no loopback interface on R4 that was natively in area 34. So we ended up choosing the first OSPF or the first interface in our OSPF interface list. Now that we understand the rule that governed the selection of the forwarding address, we're able to manipulate this, right? Because if you look at this topology, R2 and R3 has equal course paths to R4. So if we can have a loopback interface on R4, which is natively in area 34, then that becomes our forwarding address, and R1 would recurse to the path through both R2 and R3. So let's do that. Before we do that, let's actually do a trace to 4.4.4.4. Let's source this from 1.1.1. We are doing a trace from R1 to R4. So let's look at the path it takes. So we expect our very first hop to go through R2, then, so right here, R2, then to R4, right? This is because currently our forwarding address is 24.4, which recurses to this. So let's go to R4 and we configure a new loopback, interface loopback, let's say 1. And we add IP address, say 40.40.40.40, then 255.255.255.255. And let's put this in area 34. So if we put this in area 34 and we come to R1 and we look at our OSPF database, our forwarding address is now 40.40.40.40. So we are hitting the first rule because now we have a loopback interface in area 34. And if we go to R1 and look at the path to 40.40.40.40, we go through R3 and R2 because you have equal course paths. So a trace now from R1 to R4, we expect this to load share between R2 and R3. So let's look at the outcome of the trace for a minute. So 12.12.12.2 is R2. Then we have 13.13.13.3, which is R3, right? So this is one way to address this. There's another way, which we'll look at in our next lesson, all right, where we can suppress the forwarding address when we do the type 75 translation, and also instruct both R2 and R3 to do this translation. Now, if you want more details or insights into what the forwarding address does itself, let me know, and we can have a lesson specifically dedicated to that, right? So the forwarding address basically helps in optimizing routing within the OSPF network. So it allows us to route directly to an external network through a path which is closer to that destination, instead of going through the router which originated that prefix. Put in a different way, the fact that an ASBR originates an external network does not necessarily mean that we should go through that ASBR in reaching that external network if there is a better path to reach that external network. We achieve this by using the forwarding address. By default, it is set to 0.0.0.0. What this simply means is that, well, just go to the router which originated this, which can lead to suboptimal routing. But when we have the forwarding address specifically set, like we saw, and there are some conditions that has to be met for us to have the forwarding address set to the non-default. When this happens, then we are able to have this optimal routing based on paths that are closest to the destination. I hope you enjoyed this lesson. Thank you for staying with me, and I'm looking forward to seeing you in my next lesson. Thank you.